So we're going to look now at like triangular elements. So using global coordinates, and these are linear. So right now we just have three nodes. We got I, J, and K. And so this is just kind of the overall shape of that element. And then if we actually looked at the pattern of the temperature across that element, we could have something like this. So that's the temperature distribution. All right, so again, on a fin, it could look like this. We have all these triangular elements across the fin. So again, temperature can vary in both the x direction as well as the y direction. So that's why we use the 2D elements. The linear element is better suited for curved boundaries than the linear quadrilateral element because we can get in there and fit the curved boundary better than the quadrilateral element. The approximate temperature distribution in the triangular element is this. So we got three coefficients, A1, A2, and A3 to solve for. So three unknowns, A1, 2, and 3. So we need three boundary conditions, and I bet you can guess what they are at this point. All right, we're going to find the temperature. We know the temperature at node I, J, and K, and we can locate those by its position at X, global position XI and YI, J and J, and K and K. So we're going to substitute that back in and solve for A1, 2, and 3 simultaneously. All right, when we do that, we get these. So a little bit more complex than the quadrilateral elements. All right, so a lot more terms in here, but we've already solved for here the temperature at node I, J, and K. It looks like I kind of lost this bracket over here, so we can close bracket here. Where area is the area of the triangular element, and that comes from, so if we want to calculate this area here, we would take 2 times A, we could determine it from the rest of the location of the coordinates on the corners of our triangle. So rearrange that algebraically and to obtain the shape functions at nodes I, J, and K. So with our global coordinates, shape function at node I is kind of simplifying 1 over 2a. Got this alpha now, this alpha at node I, beta at node I, and the delta at node I. And so maybe wondering what those are. It's just kind of grab some terms here. So it collects these terms of x and y for alpha, for beta, and for delta. So again, simplifies it, cleans it up a bit. And the shape function properties are still enforced. In this case, they still show up in the triangular element. All right, so now we're going to look at the triangular elements. It's still linear, but we're going to do it with natural coordinates. All right, so we got, we have 0 on the one corner. And in this case, we use lambda going from I to K, and lambda is going to be 1 at K. Starting at K, we get eta. Eta goes from 0 at K to 1 at J. And then we got chi. Chi is 0 at J, and it goes to 1 at I. All right. So we have all those. We added lambda now here on, in addition to chi and eta from the past usage of natural coordinates. All right, so for our triangular elements, we use areas to find the natural area coordinates. So we have chi is our area of 1 divided by the overall area of the triangle. So let's go back here and highlight that. All right, so here's area 1. All right, so that area is made up between nodes K, P, and J. P is at the center, the geometric center of our element. And then area 2 is I, K, and P. Area 3 is I, J, and P. So that's where we're coming from for these A's that we see in the numerator. And so observation, hopefully we can see that if area is made up of 1, 2, and 3, if we add up these three guys, they equal 1. And hopefully that kind of rings a bell. These actually are the shape functions. So chi, eta, and lambda are the shape functions for this triangular element. So therefore, we'll say chi is the shape function at node I, eta is the shape function at node J, and lambda is the shape function at node K. So they're defined previously already at the linear triangular elements. You saw them with the global coordinates. So we already have those defined. All right, so pretty straightforward there. Now let's look at quadratic triangular elements. So quadratic, we're using, oops, didn't get at the end there, quadratic natural coordinates. All right, so we got this extra node here in the middle. So L, N, and M, along with I, J, and K on the corners. Right, if we do this in natural coordinates, so we still have chi, lambda, and eta up here. And you can see how we can get this curve shape. So very good element to use. So this is a 6-node quadratic triangular element. It's basically a higher order version of the 2D 3-node triangular element. So we saw this with the rectangular elements before. For the same number of elements, this element produces better nodal results than a linear 3-node element. So it kind of makes sense. You got some more nodes. You can do some curves better than the 3-node. So the approximate solution here, we got now 3 coefficients we got to deal with, a 1, 2, 3, 4, 5, and 6. And so we're going to need temperature at each one of those 6 nodes. We can solve for those coefficients and develop the shape functions, the natural coordinates. We go through the same process and we can get the shape functions at nodes I, J, K, L, M, and N. And we can see them all here in terms of chi, eta, and lambda. All right, and then we do those in matrix form if we substitute in our psi. So we'll go general here. And again, that psi can be temperature, velocity, displacement, anything that makes sense as we develop, depending on what the problem we're solving here. Sorry, this is probably the most commonly used element. Triangular element is very, very popular when people are doing grids and meshing. All right, stretch break here. Been going for a bit. Again, very repetitious. But again, if you move around and check the notes below for different times if you want to jump ahead or move back.